Hello, I am Spoon, and in this video, I will be introducing you to the Fourier transform uh, with coding through MATLAB and or Octave. To explain that whole title, I learned signal processing with MATLAB, but I'm currently using Octave here. MATLAB and Octave use basically the same language. Uh, And so whether you use MATLAB or Octave, this should be really easy to copy if you so choose. But without further ado, let us learn about the Fourier transform. So the Fourier transform is useful for analyzing and or filtering signals. For instance, if I am measuring, let's say, radio waves with some electronic component, that might be an antenna with a amplifier. In any case, I am measuring an electric signal, and let's say I want to know what kind of radio waves I am getting. I might use the Fourier transform to see what frequencies are being measured. I might see high frequency noise. I might see 60 hertz noise, which is due to, in the US, power is supplied with 60 hertz. So if you plug something into the wall, into an outlet in the wall, you will be getting 60 hertz power, maybe at 120 volts. So if you do the Fourier transform, you might see some type of signal at 60 hertz. In addition, uh, you might use the Fourier transform to filter sounds. So if I have a sound file, which is basically a vector of numbers, values, I can use the Fourier transform to see what kind of frequencies are being present or the different pitches in the sound, and I might boost the bass with the filter, which means I increase the power of low frequencies, or maybe I boost the treble, increase the power of higher frequencies. So yeah, you can. Oh, with images, I've used the Fourier transform and filtering in the frequency domain to make images more blurry or increase graininess, maybe to see any repeating structures in the image. And then for MRI, MRI is really weird. Um, the signal it measures requires an inverse Fourier transform in order to create the image. So overall, it Fourier transform used for analyzing. It's a step to filter different signals, whether it's an image, electronic signal, sound. I mean, sound is an electronic signal. You're converting pressure waves into uh, electric signal. But in any case, and then reconstructing images if you are measuring signals in the frequency domain, which is really weird for MRI. Hopefully, a lot of this will make a little bit more sense once you get to know the Fourier transform. But without further ado, let's get into coding. So the first line of my code is to clear this figure on the right, and then I'm going to define a few parameters. I'm going to build a signal to begin this demonstration. So I want the sampling frequency to be 1000 hertz or 1 kilohertz, which means that I want 1000 data points per second. Then I want n to be 10,000, which means I want 10,000 data points. Based on this information, I have defined my time vector or time points starting from 0, and with the sampling frequency and number of data points, I'm going to have 10,000 data points, 1000 data points per second, which means I'm going to have an interval of 10 seconds. This here is a windowing function. That won't make sense until later, so let's ignore that. All right, with those parameters set, let's build our signal. So I want to create a signal that is a sum of sinusoids. The frequencies of the sinusoids, well, first off, I have this set up to add two sinusoids together, but The frequencies I want to add together are this isn't 10 hertz and 5 hertz. This is saying, this is set up so that my signal will oscillate 10 times in the given time interval. So this will oscillate 10 times in 10 seconds, which corresponds to 1 hertz. Then I want another sinusoid that oscillates 5 times in the 10-second interval, which corresponds to 0.5 hertz. I don't want any phase shift, so it's just going to be a sine on top of a sine. They're not going to be horizontally moved whatsoever. I don't want a vertical shift, so this will be all nice and zeroed. And then this adds them together and stores uh, the sum as y. And then I'm going to plot it. Uh, these are the parameters I'm using for plotting. I have a custom function to make everything look pretty. And don't forget when you plot to have x-axis and y-axis labels with units. And in this case, I am creating a signal, making up a signal, and it's going to be in volts. So let's plot this. You'll notice that this looks like just one sine wave, and that's because I set the amplitude to being 0. So this basically cancels out this 0.5 hertz or 5 cycle signal part. In any case, here it is. 10 cycles over 10 seconds means 1 hertz. There's no horizontal shift. A sine wave always starts at 0, and you can see it starts at 0 here. So we have our signal now. It's plotted. Yippee. All right, let's get into some interesting properties in order to measure this signal. So let's say we have a sine wave, not cosine. I want this to also have 10 cycles in the time interval. I'm just gonna create that signal. No horizontal shift, no vertical shift. Um, this variable here will multiply this new signal with the old one, but I'm not going to plot that just yet. I'm going to get rid of that y. All right, so we're just plotting this simple sinusoid. And it overlaps perfectly because they are the exact same thing. Now, what is what is what is the product? So if I multiply this new one by the old one, I get this. So this brighter white line is the product of the two signals, and this darker orange line is the original. You see that this product is all positive, which means the area under this curve is going to be completely positive. So if I zoom in, you'll see that these aren't lines, these are all individual data points. That took a while to load. And if I multiply the first data point by the new first data point, then I do the same for every other data point that corresponds to the same time point, add them together, and then that's what this sum of product is down here. If I divided this by, what do I have to divide it by? If I divide by like the number of data points and the time interval or the sampling, whatever. But this kind of corresponds to the area. Now this will decrease if I slightly shift my original signal. Let's say that it is just a little bit off. Now my area is no longer 5,000, it is 4,045. And let's just completely shift it by a quarter of 2 pi, which is pi halves, which then transforms this into a cosine wave. Now this area is 0, the area under this product curve. Let me increase it just a little bit more. Let's say 0.3. Now the area is becoming more negative. What about 0.5? Maximized again. And so if you multiply two sinusoids together at different horizontal shifts, uh, you can maximize the magnitude of the area under the curve if they align nicely, or either they are perfectly on top of each other or flip-flopped or 180 degrees off. Now, this area thing is used as an indicator of whether or not a signal is present. Because let's say I add in my other signal. Remember, 5,000 is the maximum for this instant, sum of product or area. So let's add in another signal. Okay, so now the signal is a little bit wonky. It's not a perfect sinusoid anymore. If I do the whole area product, whatever, I still get that magnitude of 5,000. And that counts for anything I add in. So let's do 9. 5,000 again. So no matter how messy your signal is, uh, you can use this approach to begin to kind of measure whether a particular frequency is present. But that depends on the horizontal shift. And it also depends on frequency. So if you don't have the right frequency, it's really not going to work. So let's say I do, actually, let me just show, because previously I have 10 cycles, and now I'm going to have 9. Now it also lines up. But what about 11? I'm adding 10 cycles, 9 cycles, and now I have 11. Let's just see what happens, and the area is 0. All right, what about 5? Nope. What about 20? Nope. What if I just shift things around a little bit? So let's see, 5, 6. 0.1, 0.3, still 0. So if you multiply a sinusoid by a signal, it's the right frequency, it's lined up horizontally perfectly. You can see if that particular signal is present. Uh, Basically, I'm saying a lot has to line up to be nice, but there is a nice property in trigonometry which says cosine squared of theta plus sine squared of theta equals 1. So I have these ugly horizontal shifts. I have these two frequencies, and I have this nice convenient sine wave here. So I previously showed that when everything is perfectly lined up, the area or sum of product is 5,000. But cosine squared of theta plus sine squared of theta equals 1. So if I just do this once with a sine wave, the area is equal to 4,045. And if I do this again with a cosine wave instead, now it is 2,939. And if I do 4,045 squared plus 2,939 squared, and I do the squared root, or to the power of 0.5, should get exactly 5,000. So now we don't have to do that whole test a bunch of horizontal shifts. We just have to do sine, cosine, and now we know what's the maximum alignment. Now this could be more convenient if you just do, instead of multiplying by a cosine wave and a sine wave individually, multiply it by this kind of wave. So you have cosine of whatever plus square root of -1 times sine of whatever. So basically I'm taking the cosine wave and adding it to square root of -1 times the sine wave. That will result in a complex number in which the real component corresponds to the cosine wave and the imaginary component corresponds to the sine wave. The magnitude of that complex number is equal to that highest theoretical sum of product thingy. So what you just have to do is you might get a complex number. If you want to get the magnitude of a complex number, just do this. This 4,000, like if, what was 4,045 corresponding to? Well, I forget. Complex numbers come in the form of a plus b times square root of -1. A is a constant, b is a constant, and then square root of -1 is typically referred or notated as being I, J, or I like to use 1I for Octave or MATLAB. So anyway, if you use the complex wave thingy, you can, it's more convenient. And then the angle of the complex number corresponds to the phase shift of the signal with respect to a cosine wave. In conclusion, now we've simplified things. We can figure out if a particular frequency is present in a signal. The only difficult part is getting the right frequencies to measure. And so that's where the Fourier transform comes in. The Fourier transform, let me close that. The Fourier transform does that whole complex wave multiplication to find areas, and it tests it for harmonics. So harmonics are oscillating waves that fit perfectly into the window. So if I go back and I just plot the signal, let's get rid of the second component. So the first harmonic looks like this. It oscillates. Oop, let me get rid of that horizontal shift. So this fits perfectly into this 10-second window, starts and ends in the same place, and it oscillates once. And I can increase it to 2. Now you have 2, 3, 4, yada, yada, yada. And the Fourier transform will measure those harmonics up to the number of points. And we'll find the area thing in order to figure out if certain frequencies are present. And so let me just show what that looks like. So here's a vector of all the corresponding frequencies that will be tested. And then here is MATLAB's or Octave's fast Fourier transformation. The reason it's called fast is because when you do a Fourier transform, there are a lot of redundant calculations, and so this figures out how to avoid multiplying and adding the same things over and over again. And then over here is just a small factor I use to try to convert the Fourier coefficients to a number that corresponds to amplitude. This doesn't work perfectly. All right. I'm going to reiterate this one more time before I actually plot this. This Fourier transform, this is taking your signal, it's multiplying a bunch of cosine waves and the imaginary sine waves, complex waves. It's multiplying it against the signal to see where things line up nicely. And when it returns large values, that means that one particular frequency is pretty present. And so let me start with my 1 hertz signal. So this is 1 hertz. Now I'm going to do the Fourier transform. And now it's returning all of those areas or sum of products. I was previously getting 5,000. It's returning Fourier coefficients, which are complex, but the magnitude corresponds to that whole area thing. And so since I have a 1 hertz signal, there should be a peak at 1 hertz. So let me zoom in. Let me zoom in more. My head is a little bit in the way. But yeah, you can see there's a peak at 1 hertz. Now let's try doubling the frequency. So there should be something at 2 hertz. Let me zoom in some more, zoom in a little more, and we have it at 2 hertz. So this is saying when things are just lining up right, then you get a large value back, and that's why there's that spike at 2 hertz. Let me introduce another frequency. So let's do 1 hertz and 2 hertz. I have the amplitude on. There should be 2 peaks now. Let me zoom in. There you go. You have your 2 peaks. You might have noticed that on the other side, you're also getting the same thing. The Fourier transform for discrete data it produces Fourier coefficients that have symmetry. The reason for this is due to something called aliasing. So if I go back to this signal, let me just go back to 10 hertz again. So you have an obvious oscillation. Let me increase it a little bit more. Doubled. All right. Now let's double it again. It's starting to get really crushed. Let's double it again. It's getting really crushed again. But if I zoom in, you can still see there's some oscillation. And now these dots are getting more apparent. All right, let's double it again. Now it's starting to get a little bit harder to see this oscillation, and that's just because um, there's only so many data points per second. So let me just make this ridiculously large. Now it's starting to look really strange. How about even larger? So you see there's some limitations to having a particular sampling frequency. The larger it is, the less weird stuff you see like this. What I'm trying to do is show the aliasing though once you reach a very high frequency. Now you're just seeing this should be an extremely high frequency, but now it's starting to look like something that's a little bit lower. And now at this point, it looks like the frequency is 2 hertz. I mean, 2 cycles, which corresponds to what, like 0.2 hertz, even though the frequency is actually large. And that's aliasing. That's because your cycles are so close together that your sampling frequency can't show the oscillations individually. And so it gets to a point where it's just kind of sampling not within the cycles, but every few other cycles, which causes this aliasing, which means you're starting to see patterns that aren't actually there. So this should look like just really, really fast oscillations, but now it just looks like this. Because of this, when you get frequencies that are higher than the Nyquist frequency, the Nyquist frequency is half of the sampling frequency. Once you start getting above that, it kind of looks like higher frequencies start to look like lower frequencies. And that is why when you do the Fourier transform, it is kind of symmetrical. It's because of the aliasing. It's starting to think there's this high frequency, but really the sampling frequency won't allow you to actually measure anything higher. So in truth, what really matters is seeing anything up to the Nyquist frequency, which is half of the sampling frequency. So this is what you really should be looking at. Anything after 500 hertz, half of the sampling frequency is just a reflection. You also might see plots like this where you have a frequency plot in the terms of a log scale because it makes some things easier to see. So 10 to the power 0 is 1, so you're seeing a peak at 1 hertz. Finally, I wanted to show you something called spectral leakage that doesn't have to relate to ghosts. It relates to something about signal processing. So let's say everything we've been looking at so far have been sinusoids that fit perfectly into the window we are looking at. But what if it doesn't? What if instead you have it kind of is halfway. So this is showing 10 and a half cycles. It's not an integer. That results in spectral leakage. So previously, you saw this nice spike, but if I get things a little bit off, now that spike is lowered and spread out, and then a spectral leakage. That is when you have frequencies that are not harmonic of the window you are looking at. Now, this can cause some problems where spectral leakage makes it really hard to see those spikes. So you might use something called a windowing function. So over here, I introduced this. I didn't actually introduce this. I just acknowledged that it exists. This is a windowing function where you multiply it by your signal. It preserves the center of the signal, but as you go out towards the edges of your signal, it attenuates it. So it kind of looks something like this. This. So it preserves the center and it kind of attenuates it. And this avoids the issue of when things don't fit in perfectly. And so let me show a before and after the frequency domain plot. So you have this is kind of like a spread out peak. And now I will incorporate the windowing function. And now it does reduce the height of the peak, but it makes it more distinguished from the outside area. A windowing function is useful, but there is a pro and a con. The pro is that it can make certain frequencies stick out when they are hard to see due to spectral leakage. The con is windowing functions can make it hard to see two frequencies that are close together in the frequency plot. Oh shoot, I think there's one other thing that was a con. It can make, yeah, it reduces frequency resolution, makes it hard to see two separate peaks if they're close together. And then I also showed how it reduced this peak a little bit. Yeah, that was the second thing. It just reduced the peak a little bit. So yeah, this is the Fourier transform. It allows you to look at the frequency content of a signal. I showed you the concepts behind how it's found and how if you multiply different sinusoids, you can get zero areas or a spike in area. And yeah, I hope you liked this video. If you have any questions, feel free to ask me. Um, I did not go over the actual function itself. Actually, I think I have it right. Yes, I do. So I didn't go over it specifically. So you might be looking at this and say like, spoon, what's going on? This doesn't look like anything you talked about. That's okay. Like this right here actually corresponds to the whole cosine plus I sine thing I was talking about. There's also more to frequency analysis, like what are the different types of filters that use the Fourier transform, or how do I increase the frequency resolution? You can use zero padding, but that has its own pros and cons. Yeah, I hope you have a introduction, and now you get to see how this is implemented with code. But yeah, if you have any questions, I will do my best to answer them. Thank you for watching, and I hope you have a great day. All right, now I got to pull up the Zoom toolbar, which is hard to grab. All right, bye.